Today we are going to discuss measurement. What do you mean by measurement? What is a physical quantity? What are the requirements for selection of a standard of measurement? Whatever we take as the standard of measurement, or we call it as the unit, what are the requirements for its selection? What are the different systems of unit? And why we have adopted one system of unit and then we have changed to the other system of units. So we'll see why we have made so many changes there. Like we had earlier FPS system, then we adopted CGS, then MKS, and now we are using SI. Then we'll see what is International System of Units, or SI, and what are the different base units used there, and what are the supplementary units in SI. We'll see SI definition of the base units. Then we'll see what are the advantages of SIs. So first of all, let's see what is measurement. Measurement is a process of comparison of a given physical quantity in terms of a standard of the measurement for that physical quantity. Then we'll see what is a physical quantity. Physical quantity is one which can be measured. That means anything which we can measure, that will be called as a physical quantity. But at the same time, anything which cannot be measured will not be taken as physical quantity. We can measure mass, we can measure length, we can measure distance, we can measure volume, we can measure time. So all these are physical quantity. We cannot measure emotions, so it will not be a physical quantity. We cannot measure fear, so it is also not a physical quantity. So anything which can be measured will be called as a physical quantity. So physical quantity after measurement, that means after its comparison with a standard of that physical quantity, we express it as x equals to nu. X is the physical quantity. So this is the physical quantity. N is the numerical value, and U, this is the unit of measurement. Measurement of that physical quantity. For example, suppose I have measured the length of a body and it comes out to be 5 meters. So that means length is the physical quantity, meter is the unit, and its numerical value is 5. That means the given length is 5 times the standard of the measurement of length that we have taken as the meter there. So it is 5 times meter. Similarly, if the mass we take for any particular body, suppose it is your 2 kg, it means in terms of kg, it is 2 times of that. So the given mass is 2 times the standard of mass used there. So this is how we can express a given physical quantity in terms of the units. Now, same physical quantity can be expressed in different units. So a given physical quantity can be expressed in different units like N1 U1 or N2 U2. Here, U1 and U2 will be the 2 different units, and maybe in 2 different systems. N1 and N2, these are the corresponding numerical values of this physical quantity. So for example, suppose length is your 5 meter. The same can be written, length of 5 meter can be written as 500 centimeter. So that means here meter is the unit, the numerical value is 5. When we have taken centimeter, the numerical value is 500, that means it is representing your N2. Similarly, for mass, we can take 2 kg or we can write 2000 gram. So the gram and kg will be the units there, and 2 kg or 2 and 2000 will be the corresponding numerical values. If we have a given physical quantity, so for given x, what we can write, as we have x equals to nu, so that implies if this is constant, that means it is a given x there we are taking, given physical quantity, so n will be inversely proportional to u. What was n here? N was the numerical value and u is the unit. So this indicates that if the unit is a small, numerical value will be large. And if a unit is large, the numerical value will be small. This you can see here. If we have length measured as 5 meter and expressed also as 500 centimeter, so meter is the bigger unit, so numerical value is a small 5. Centimeter is a smaller unit in terms of the meter, so here the numerical value is large. Similarly for kg and gram also you can take. So if the numerical value we take, it will be inversely proportional to size of the unit. If the unit is small, numerical value will be large. If the unit is large, numerical value will be small. Let's now take how we select the standard of measurement. What is unit? Unit is the standard of measurement of the physical quantity. So how we select anything as the unit or a standard of measurement of the given physical quantity? What are the requirements for that? So to discuss what are the requirements for selection of a standard of measurement, let's just think in this way. Suppose in a given class, it is said that all the students should have their notebook of a particular size, and they have shown one copy or one notebook, and they say, or it is said that you all should have the notebook of that particular size only. Size is not mentioned on that book, on notebook. And suppose there is a departmental store where the copies of all different sizes have been put on display. You can go and select the copy of your requirement. You can choose it and purchase it. So if suppose just a copy is being shown as a sample copy and you have been told to get the copy of that size from next class, how will you do that? And let's imagine that you all have not brought the scale at that time. You don't have the scale at that particular time when the sample notebook have been shown. In that case, you can take help of the palm. You can use your palm to take its length and breadth and get the copy of that size. Okay. But some of you may say that the palm sizes are different. Of course, it will be different from person to person. But if you all are taking measurement using your own palm, and then you are going for the shop and getting the copy of your requirement, next day you all will have the copy of that particular size, which is same for all the students, even if your palm sizes are different. So now, if we all have this wonderful instrument of measurement, why we go for the scale? Once you try to understand this, definitely you will be able to know what are the requirements for selection of a standard of measurement, and you can write that requirement in your own language, or you can visualize that what should be the requirement. One practical difficulty will be there if you are using your palm size, that whatever measurement you have taken, it will be valid for you only. You can't send someone on your behalf to get the copy of that size, because the palm sizes will be different. So what we can conclude from that whatever we select as a standard of measurement, it should not vary from person to person. In fact, there is one incident that is said that a long time ago in Egypt, in one of the kingdom, the king has said that his hand size will be used as a standard of measurement for length. So in that case, since he has said that his hand size will be taken as a standard, everyone used that. But now you just imagine what practical difficulties might have been faced by people of that country. Because this system is not prevalent. This system has died just after that particular king. So first problem might be there, that even if suppose we take the king's hand size as the standard, that means we are not allowing persons of that kingdom to take the measurement using their own hand size. So their length size is common for all. But the problem is that if suppose we have to take any measurement, either the king will have to go to the site of measurement or the things will have to be brought. Suppose there is any dispute about the length of a body, the thing can be brought to the king. But if there is any dispute regarding the land size, in that case we cannot bring the land to the king. King will have to go there. So what we conclude from that, whatever we select as a standard of measurement, it should be easily available at all places, or it should be easily reproducible. Second thing, with time or with age, hand size will change. Of course, for adult, there might be very small change, but still there is a change. So in that case, the whole measurement will be wrong. What we have taken now, and it will not be valid after a few years. So that is another problem. Second thing is that what will happen after the death of the king? Because after the death of the king, that particular standard of measurement will be lost. So whatever we select as a standard of measurement, it should not change with time, or it should be reproducible at any moment. So these are certain things which are the requirements for the selection of a standard of measurement. So let's discuss that one by one. So the requirements for the selection of a standard of measurement are, it should be well defined. What do you mean by it should be well defined? Like whichever we are taking as a standard of measurement, its description should be complete. Just for example, suppose you are using your palm for taking measurement. So when we are taking measurement, then it should be very clear what we have taken for the measurement, whether it is the distance between the tip of the thumb to the middle finger, or the tip of the thumb and tip of the forefinger, or ring finger, like that. So it should be very clear, because once you have taken measurement, suppose by taking the tip of the thumb and the tip of the middle finger, and at other place you are taking measurement by taking distance between the tip of the thumb and forefinger, the whole measurement will be wrong. So when we define the term for selection of a standard of measurement, it should be properly and should be well defined. Second thing is that it should not change with time or physical factors. With time, it should not change. That is why we cannot take anyone's hand as a standard there, because with time or age, it will be changing. Second thing is, it should not change with the physical factors also, like temperature, pressure, or any other physical conditions. Suppose we take a metallic scale and we are using that one. In summer, when the temperature will rise, in that case, there may be expansion in that metallic scale. So the measurement made with that will be different from its actual measurement. It is possible that 100 centimeter mark made on the metal scale, due to expansion, suppose it gets increased to 101 centimeter. Of course, it will not be that much large, but just to imagine, Suppose it gets expanded to 101 centimeter. So the scale length will change, calibration separation will change, but the calibration will just remain 0 to 100. So what you will measure as 100 centimeter with that scale will actually be 101 centimeter. Similarly, in winter, when the temperature decreases, in that case again there will be different value of the measured length and actual length. So it should not change with physical factors, or if it is changing, we should know what can be the calibration done or what can be the correction done to get the exact measurement. Then it should be of suitable size. The unit which we are using, it should be of suitable size. That means it should not be too small, nor it should be too large. Next is, it should not change with person to person or place to place. Whatever we select as a standard of measurement, it should remain same for everyone. It should be same for anywhere, at any place. Then it should be easily available at all places, or it should be easily reproducible. Whatever we select as a standard of measurement, we keep one copy of that. Normally in the system, SI, they keep one copy of the standard of measurement at the international forum. Then they make a copy of that and give it to the different participating countries which are adopting that particular system of units, and just kept there in their national laboratory. Then from that, any particular country will make a copy of that and distribute to the different weight and measurement department throughout their country, so that it is made easily available at any place to any person. So that if there is any dispute, any doubt is there regarding any measurement, it can be easily verified at the local level, or if it is required, they can go to the other cases to justify that or to check that whether it is correct or not. So it should be made easily available at all places. What do you mean by easily reproducible? Suppose we have adopted one particular length as meter. It is kept at the international forum. This is one particular place where it is kept. So, and the copy of that is distributed everywhere. Suppose due to any reason that particular place get devastated, maybe due to earthquake or any other reason. If that place get devastated, that system of unit will also be lost. So now if there is any dispute between any participating country, no one will be there to verify or justify that, which is the correct one. So whatever we select as a standard, we just select in such a way that we can reproduce that unit at any place at any time. Like for the standard of measurement of length, what we take it as meter, it is taken as the distance traveled by light in a particular duration of time in vacuum. So we can get light at any place. We can see what is the distance traveled by light in that particular duration which has been adopted, and that particular length will be meter. So we can produce that particular standard of measurement at any place. And lastly, it should be accepted by all. Obviously, any particular system where the problem will not be there, or the shortcomings or the doubts which are there, if it is removed, definitely all will be accepting that. And if any particular system is accepted by all, it can be used for all different participating countries there or by the people of that country. So these are the requirements for the selection of a standard of measurement. So the different systems of unit which we had, they were FPS system, CGS system, MKS and SI. In CGS, we have the units like foot, pound and second. In CGS, we have centimeter, gram and second. In PS, we have meter, kilogram, and second. Whereas in SI, we have 7 base units and 2 supplementary units. But before we go for SI, let's discuss why we have moved from one system of unit to another. Like we have adopted earlier FPS system, then we changed to CGS. Then from CGS we shifted to MKS. So why we have changed so many different systems of unit? And nowadays we are using SI. So even we have changed from MKS to SI. The main problem was with FPS system that their units were abrupt or they were like the random one. That means conversion of units from one to its other unit, subunits or multiple, was a random one. In FPS system, we have foot as the unit for length, and one foot has 12 inches. Then 3 feet makes 1 yard. If you have to change from mile to yard or foot, then we'll have to use those conversion factors and we'll have to multiply them. Like if you want to know in 1 mile how many inches are there, so we'll have to multiply to 3 and then to 12 so that we can get the number of inches there in 1 mile. So this conversion from one unit to its subunit or its multiple was a difficult one. So we changed to CGS system where it was the metric system adopted, where all units, they differ with their subunits or multiplier by a factor of 10. Like we have the milli, centi, deci and other, all changing by a factor of 10. So here the conversion was very easy. Like if you want to convert 1 meter to 1 millimeter, so we can easily convert 1 meter to 1 millimeter, 2 millimeter by just taking a multiplying factor of 10 to the power 3. If you want to convert 1 meter to centimeter, then it is your 10 into 10, that is 10 to the power 2. That will be the multiplying factor. If you want to know 1 meter is how many kilometers, so we can easily take it as 10 to the power minus 3 kilometer. So conversion from one unit to its subunit or its multiple was very easy there in metric system. So we adopted centimeter, gram and second in system there, which is based on the metric system. So we adopted CGS system where it is a metric system. But the problem with the CGS system was the units used in CGS system like centimeter, gram and second, they were very small units as compared to the day-to-day life measurement which we come across. But from CGS we shifted to MKS just because the units used in CGS were very small, like centimeter, then gram, which we are taking. These are the small units in comparison to the measurement which we come across in day-to-day life. Like in day-to-day life, we have the kilogram as the convenient unit there for the measurement of the mass there. Similarly, meter is a convenient unit for measuring length. So we changed from CGS to MKS where the units were relatively larger and they were of suitable size as compared to measurements made in day-to-day life. But the problem with the MKS system was that they were not absolute one. They were not the complete one. Here, definitely advantage was there that it was based on the metric system. It is having units which are of suitable size. for the measurement of day-to-day life. Observations are the measurement there. But for many physical quantity, there were no units given in MKs. There were no units given for amount of substance. There were no units there for luminous intensity. So we look for a system of unit where all these physical quantities can be assigned some unit. Another problem with the MK system was, for many physical quantity, there were more than one units. There were many physical quantity for which there were no units, but at the same time there were many physical quantities for which there were more than one unit. Like for energy, they have the unit as joule, but for heat it was given the unit as calorie, although heat is a form of energy. So for same physical quantity there were two units assigned there, which was your joule as well as your calorie. Similarly, there were the units given for the charge and magnetic charge, there are magnetic poles separately there. We have the electrostatic unit of charge, we have electromagnetic unit of charge there. So there were the different units given there. Whereas you know that electricity and magnetism, where we know that electrostatics and magnetism, electrostatics deals with the charges, whereas the magnetism, we take that it is dealing with only magnets, but it's not like that. Moving charges produces electric current, and electric current can produce magnetic field. So then it was found that if the magnetic field is being produced by current, definitely the current is the one which is the most suitable one, which can express even the electrostatics or the charges there, as well as it can deal with the magnetism. So there were no requirement for two different units mentioned there as electrostatic unit of charge, electromagnetic unit of charge. So these were rectified in SI. In SI, we have 7 base units and 2 supplementary units. So the base units in SI are kilogram, that is the unit for mass, meter, unit for length, second, unit for time, Kelvin, unit for temperature, ampere, that is the unit for electric current, candela, unit for luminous intensity, mole, unit for amount of substance, and supplementary units were there. 2 supplementary units were there in SI, that is radian, that is the unit of plane angle, and steradian, that is unit of solid angle. Now all these have been given a specific definition in SI, like meter, second, kilogram, all have been given or defined in a specific manner. So the definition which is adopted in SI for all these, that is a very important one, and you all must know what is the definition or SI definition for these base units. Take SI definition of base units. Like for kilogram, it is the mass of a platinum iridium cylinder whose diameter is equal to its height and is kept at Sèvres near Paris. It is just a prototype of a cylinder made of platinum iridium which is kept at Sèvres. So mass of that prototype is taken as kilogram. Then SI definition for meter. It is the distance travelled by light in vacuum in 1/299,792/458th of a second. In this much duration of second, whatever is the distance travelled by light in vacuum, that will be 1 meter. And here do remember that mentioning that distance travelled by light in vacuum in this duration is must, because light has different speed in different medium. So in vacuum only, if you are taking in this much duration of time, distance traveled by light, that will be 1 meter. Now you can easily identify the importance of this particular number, 299,792,458 of a second. In this much duration, light has traveled 1 meter. So in 1 second, how much distance light will travel? That will be equals to 299,792,458 meter. And that is the distance traveled by light in 1 second. So it is this much distance in 1 second. And now you see this particular number. If I take this as the distance traveled by light in 1 second, that means it is its speed. And its speed can also be written here. Like if I put decimal and express it in terms of the power of 10. So it is your 1, 2, 3, 4, 5, 6, 7, 8. And if I put the decimal here, that is 2.9, then it can be written as 10 to the power 8 meter per second. This particular number, 2.99792,458, is roughly taken as 3. And this is your 10 to the power 8 meter per second. That means the speed of light in vacuum, which we take it as 3 into 10 to the power 8 meter per second, is basically its rough value. Exact value is this much. So that is the speed of light in vacuum. For the definition of second, it is the time taken in 919, 26, 31, 770 cycles of vibration of cesium-133 in its ground state when unperturbed by any external field. When no external field is acting on cesium atom, then in its ground state, whatever is the time taken to complete this much number of oscillations, that will be 1 second. So this is the definition of second. And you can also see that you know how long is 1 second. And even in that 1 second, cesium atom has completed this much number of oscillation. So you can just imagine how fast it is oscillating or vibrating in its ground state. Let's now take SI definition of Kelvin. It is 1 by 273.16 fraction of thermodynamic temperature of triple point of water. Triple point is the particular temperature at which the substance, like if it is the triple point of water, then it will exist in all the 3 states, solids, liquids and gaseous state. So Kelvin is 1 by 273.16 fraction of thermodynamic temperature of this triple point of water. Then definition of ampere. It is the constant current which when passed through 2 straight parallel wires of negligible area of cross section and of infinite length placed 1 meter apart in vacuum, which produces a force of 2 into 10 to the power minus 7 Newton per meter length of it. We have 2 wires of negligible area of cross section and of infinite length, which are placed 1 meter apart in vacuum. And if they produces a force of 2 into 10 to the power minus 7 Newton per meter length, then the current which is passing through those wires, that is taken as 1 ampere. In fact, in class 12, when you will do force between 2 straight wires which are carrying current, which are placed at some distance apart in a medium or in vacuum, there is derivation for that force. And from that expression, we also see how we can define the unit of current. And we get the definition of current unit, that is ampere, from that mathematical expression. And this is the definition adopted. Now, SI definition of candela. This is the unit of luminous intensity. It is the amount of luminous intensity in a given direction of source which emits monochromatic radiation of frequency 5.4 into 10 to the power 14 Hertz and has a radiant intensity of 1 by 683 watt per steradian in that direction. So that much amount of luminous intensity, we call it as 1 candela. Similarly, for mole, if you take its SI definition, it is the amount of substance which possesses same number of entities as possessed by 0.012 kg of C12 atoms. This is number of entities, that means items. The number of entities or the items must be the same. So whatever amount of substance which we are taking, which possess same number of entities, it may be same number of atoms, same number of molecules, same number of protons, same number of electrons, and which is possessed by 0.012 kg of C12 atom. So that much amount will be your 1 mole. And do remember that when you are defining it, this is your 0.012 kg, you could have written it as 12 gram. But since we are using SI definition, in that case, the all units which we are using must be expressed in that system. So we write it as your 0.012 kg and not 12 gram. Now the definition of supplementary units. Supplementary units we have used as radian and steradian. Radian for plane angle and steradian as the unit for solid angle. So radian we define as the angle subtended at the center of a circle by an arc equal to the radius of the circle. Because here we define angle, suppose if you have taken, this is the part of a circle, radius is r and length of the arc is L. Angle subtended at the center is theta. So we define angle as the ratio of length of the arc by radius. If we take L equals to R, that will give theta as 1. And the unit of this angle, we take it as radian. So 1 radian will be there when the length of the arc and radius, they are equal. So that is how we have defined radian there. Similarly, for steradian, which is the solid angle, unit for solid angle there. So this we define as the solid angle subtended at the center of a sphere by a surface of the sphere which is equal to a square of the radius of the sphere. Like suppose we have a sphere and this has a radius, suppose r. We take a small area on its surface. You join all the points on the circumference of this surface to the center. So what type of shape we'll get? We'll get a cone. And if it is the cone, the angle subtended at the vertex of this cone, that is the solid angle. So this is the area, suppose S, and radius is r. So the solid angle here, if I take, this will be your S by r square. Now you can easily see, if I want to get the unit of this one, if S and r square are equal, then solid angle will be 1. One steradian will be the angle subtended by a surface whose magnitude is equal to a square of the radius of the sphere. So this is how we define steradian. Let's take what are the advantages of SI. First is that it is a metric system, it is coherent, it is rational, it is internationally accepted. So let's take one by one. It is metric system. We have already discussed that here all units, they differ by their subunits or multiples by a factor of 10. So the conversion is very easy there in the system. So this is your metric system. Second is it is a coherent system. Coherent system means here this particular system has the units which is adopted in such a way that we can get the unit of any physical quantity just by a combination of these units, simply by their multiplication or by division. So just by using these units used in SI system, we can get the unit of any physical quantity. So this is your coherent system. We don't need any other system, or there is no units there which cannot be defined units used in the system. Then it is rational system. As we said that in the previous systems, we have many physical quantities for which there were no units given, whereas many physical quantities were there for which there were more than one units. But in this system, we don't have such type of problem there, or it has been a rational system indicating that all physical quantities and their units have been treated equally there, and they have been treated uniquely. And the last one is that it is internationally accepted. This system is being used internationally by most of the countries there. So if the system is adopted internationally, definitely to trade with between the different countries, it is very convenient there. You don't have to express the units used in one country and unit used in the other countries separately there, so that you have to find the conversion there. So if the same unit is being used in the participating countries, then the trade will be easier there and it will be convenient one. And of course, any particular system will be internationally accepted, or it will be accepted by all if it does not have any problem there, it is not having any shortcomings there. So SI system is the one which have no such shortcomings, and that is why it is internationally accepted. So these are the advantages of SI.